ammonia can decompose into nitrogen and hydrogen gases. And in this first example, we're going to determine the rate law, the order of the reaction, and the value of the rate constant. We're not going to do it using the method of initial rates as we did before. We're going to use the graphical technique that was described in the introduction podcast. Now here's data that was taken for concentration as time changed. And we're going to step through the different orders we discussed: 0, first, and second. There's the mathematical equation that describes zero-order kinetics. We'll take the data and plot the ammonia concentration as a function of time and go from there, see what we can get. We need to do a best fit line to see if it really is linear. You can draw it by hand using a ruler, or in our Chem 1 classes in lab, we did a number of graphs and we talked about how to determine a line of best fit. We used a linear least squares procedure. And so that's what I've done here. Does that line look like it represents the data? Well, I think it does. There's a little bit of wiggling around the line, which is what's expected, but the data doesn't look like a curve. So you might think, hey, let's stop here with zero order, since that's what it appears to be. And it does appear to be that. But we're going to go ahead and look at the data using first order and second order kinetics. This way, you can see what to expect. If we want to look at the data using first order kinetics, we need the natural log of the concentrations. There's the mathematical relationship for first order kinetics. And we'll plot natural log of the concentrations as a function of time, and then look at the graph. Does that data look linear to you? Well, let's get the line of best fit and see. Look at the data with respect to the line. When you start off at time 0, the data is below the line. And then as you go from left to right, the data goes above the line, and then it drops back below the line. That suggests that the data is really a curve and not linear. So I should not have plotted that line, which means it doesn't appear to be a first order reaction, which is what's expected. The zero order data fit a straight line, so we go, hey, it's zero order. Well, it can't be zero and first order at the same time, so this shouldn't also be a line. Let's now look at it using second order kinetics. And to do that, I need the reciprocal of the concentrations. Now there's the mathematical relationship for second order kinetics. And we plot the reciprocal concentrations as a function of time. Does that look linear? When I lay the best fit line on it, this is a little more obvious that it's a curve. The data going from left to right starts above the line, goes below the line, and then goes back above the line. Which again is expected because the zero order best fit a straight line. So before we figure out the order, the rate law, and the constant, let's look at the three graphs just briefly. The one on the left, that one best fit a straight line. And then look, first and second order did not fit a straight line, which means this data appears to be zero order data. It can't fit a straight line for all of them. Now, if none of these best fit a straight line, then you could continue on. You could use this method, go on to third and higher orders. You could investigate fractional orders. But for the purpose of simplification, we're just looking at 0 first and second order. They can't all be a straight line. That's really important. Right, so here's the straight line data. And that was 0 order kinetics. So remember why we did this. First, this lets us figure out the order. Since it's 0 order, there's the rate law in the upper right, because its rate is K times the concentration of ammonia to the 0 power. Well, that's a 1. That factors out. Now, what did the graph get us? Not just the order, but remember what we get from it. We get the slope. Now, the units for the slope are the y units over the x units. And you can either write this one as molarity per second, or you can do moles over liter second. It doesn't matter to me which way, because I take both of those as equivalent. So let's go back to this. Now the slope. What's the slope telling us? Well, look at the mathematical relationship for 0 order. Look at K. Minus K is the slope. Therefore, we pull out the slope, but we take the opposite sign, and we have our rate constant. We know it's 0 order, we have the rate law, and we have the rate constant. A reminder, rate constants are always positive.